Well, hi there. I'm Matt Adams with Loupe, and I'm really excited today that you're joining me for the start of this series on temperature control. Now, it's a really broad topic, so what I wanted to do is introduce some fundamentals of PID controllers today, and I think this is going to serve as a great foundation for some of the more advanced topics that I'll be covering later. So if you're not familiar with PID controllers at all, or maybe you just need a refresher, you're in the right place. In most temperature applications, there's a heating element that's used to maintain a set temperature on part of a machine, and this is typically done by powering that heating element with AC line voltage. It's often a design criterion to reach temperature quickly upon a machine startup, so the heating elements are sized such that if they were powered on all the time, they heat up far beyond the useful temperature. To set a percentage of their capacity, relays turn on and off based on a duty cycle. For example, a duty cycle of 20% over 5 seconds would have the relays be on for a second and off for 4. And ultimately, the controller we're designing will continually update the correct duty cycle to maintain its desired temperature set point. Now, in a closed loop system, there's a target set point temperature that's compared against the measured temperature. And the difference between those two is the error. And it's this error and this error alone, which is the input into the controller. Since controllers continually update the duty cycle, it's helpful to have some charts showing how the temperature, shown in blue, and the duty cycle, in green, change over time. The simplest control systems are proportional. They set the duty cycle by multiplying the error by a constant value called a gain. A larger error will have a larger duty cycle. And this idea has a lot of good things going for it, because when your temperature is far away from the set point, you have a high duty cycle, but when you're getting close, the duty cycle drops down. This system here has a set point of 100 degrees, shown in purple, and the system starts out at 0, so the starting error will be 100. With a proportional gain of 0.5, the duty cycle will start at 50% and drop down as the temperature rises. But we have a glaring problem. The temperature never reaches the set point. It actually levels out around 60. This perpetual difference is known as the steady-state error. And that's an interesting property of using purely proportional gain with temperature control. Your duty cycle will eventually just match the heat that's being lost to the colder environment, and will always have a steady-state error if the controller is stable. Though increasing the gain, as I show here, can reduce this error, it's rarely good enough for high-performance industrial control systems. And you see as I increase the gain, eventually the system will become unstable, alternating between fully on and fully off with these wildly swinging temperatures. Fortunately, there's a solution to eliminating the steady-state error, and it's by adding an integral component. The integral accumulates the error history over time, which is effectively this area between the set point and the actual temperature. As an integral component is added to the controller, you can see that the system error decreases over time, and this is exactly what we want. Now, in many controllers, the integral gain, sometimes called the repeat time, has a unit of seconds. When we review the standard form of a PI controller, we can see that this accumulated error, shown here as the integral, is multiplied by the inverse of this integral time. This means that a lower integral time has more impact on the I component. And we can see this in action as I gradually decrease the integral time here. This leaves us just with one remaining challenge. You see, in order to get up to temperature quickly, often the gains need to be increased until it introduces some slight overshoot. And in order to compensate for this, we need a way to pump the brakes. And this is done with the derivative component. The derivative adds a value that's proportional to the slope of the error. And this is great because when you're approaching the set point, the slope is negative, and this adds on that negative component that we need for our brake. So let me go ahead and add some derivative gain into this system. And we'll see that as the derivative time increases, my overshoot decreases. This is exactly what we want. And I see here that there's a little bit of overshoot remaining, and I can dial that back in a smidge by adjusting the integral, and then we have it. We have a well-tuned system around this set point with a PID controller. Let's go ahead and wrap this up with a quick review. The output of a PID controller is the sum of its three components. The proportional element has a linear relationship to the current error, the integral component has an inverse relationship to the accumulated error history, and the derivative is linearly tied to the current slope of the error. By increasing the proportional gain, we can decrease the amount of time it takes to get up to temperature, and decreasing the integral time helps eliminate the steady-state error. Increasing the derivative time pumps the brakes and reduces the overshoot. And we can see all three of these things play out in our example here. Initially, our system was primarily driven by the proportional component because of that large error we started with. But over time, this error accumulated into the integral component. And as we neared the set point, the derivative pumped the brakes to ensuring there wasn't substantial overshoot. Now, the not so big secret is that while PID controllers are a great choice in a lot of applications, they're not without some caveats. So I hope you'll stick around for the next video where I dive into some of these cases a little more and show you some ways to enhance your controllers.